Hello everyone, this is the solution to the Washington Gold 2020 HMMT and PMAC TST Problem 6. We have an equal angular hexagon A, B, C, D, E, F. Here you'll notice in the diagram that I've extended the side lengths to obtain an equilateral triangle with sort of three smaller equilateral triangles. And the reason we can do this is because each interior angle of the equal angular hexagon is 120 degrees, which means that if we extend the side lengths, the marked angles in blue are all going to be 60 degrees. And this is helpful for two reasons. The first one is it gives us a way to compute the area of the equal angular hexagon. And you'll note here that that's exactly what the problem is asking for. And the way we do this is to calculate the area of the large equilateral triangle here, which is XYZ, and then subtract the area of each of these smaller equilateral triangles. The second thing is you notice that the opposite side lengths of the equal angular hexagon are actually parallel, because, for instance, if you take BC and EF, you'll notice that BC is parallel to the side of the bigger equilateral triangle XY by the corresponding angles, which means that similarly you get that BC is parallel to EF and so on. And this will come in handy a bit later. And now I guess we can start trying to look at how we can solve this problem. So here we're given these three side lengths as well as this extra condition that the diagonals of the equal angular hexagon intersect at some point, let's call it G. So usually if we're given, say, a fourth side length of the equal angular hexagon, let's say we know the value of x here. This is a very easy problem in terms of solving for the area of the equal angular hexagon. The way we would do that is by using the structure of the equilateral triangles here to find the other side lengths. And I claim that if we're given four side lengths of the equal angular hexagon, we can actually determine what the hexagon is without the condition that they intersect, or the diagonals intersect at some point. The way we do this is just to note that this is just for example, but you'll note that we can complete the side length of this smaller equal angular or equilateral triangle here as well as here. And from here we can know that the big equilateral triangle has side length 28 plus x, which means that dy has side length 9 plus x, and we can continue. I'll not orate all the details, but basically you can be assured that I can find all of the side lengths. And I'll erase this now because it's not going to be too relevant, but basically you can be assured that if you know what x is, that will give you all the information you'll need to solve this problem. So we want this value of x, but we're not given the value of x, and we're trying to translate this property that these opposite diagonals intersect at one point G to some property that would allow us to calculate the variable x. And now we'll go back to the comments we made at the beginning of the solution. Notably, we noted that the opposite side lengths of the hexagon were parallel to each other. And this ends up being the crucial observation that will help us solve this problem. So, in particular, we can get that there are three pairs of similar triangles, and we can use those pairs of similar triangles to sort of generate some ratios between the triangles and their side lengths, and that will let us calculate the value of x, I claim. I'll go through sort of like an intuitive, this is like the first time I've seen this problem and I'm trying to solve it sort of solution, and then I'll give you a bit cleaner of a solution that is a bit more contrived but looks nicer, I guess. Alright, so let's think about how we can try to solve given three pairs of similar triangles. First, I'll write down the pairs of similar triangles. They're a result of the parallel lines, so by angle-angle symmetry, you can get that AFG is similar to CDG, or DCG. ABG is similar to DEG, and BCG is similar to EFG. And so you can say, for instance, let AG, the side length AG, be some variable y times x. by similar triangles, we can get that DG is going to be 11 times x, and if we say that this is like some variable z times x, then we can get that this is also 11 times z. This is because of, well, this should be 11 times y actually, sorry. But that's because of the similar triangles. And we can continue chasing these side lengths. You'll get that because the ratio of CG to GF is 11 over x. The ratio of BC to FE is also 11 over x. So this ends up being x over 11 times 8. And if we consider this final pair of similar triangles, BAG and EDG, we can get that this is going to be 20 times 11 over x, because the ratio DG over AG is 11y and yx. And from here, we can use, I guess I'll just label another variable for this. If we have some w, and this would be 11w, then this would have to be, because of the similar triangles EDG and ABG, you get that this is 11w, and this is going to be x times w. But if we have this is x times w and this is 11 times w, we'll run into an issue. I guess just to confirm that this is the case, we can note that now these two triangles have corresponding ratios. But the reason this arises as somewhat of a problem is because we also have this pair of equal similar triangles that we started with. And here we would instead have that the ratio FG over CG. So CG over FG is equal to 11z over zx, which is just 11 over x. But also this is equal to BG over EG, which we already computed to be x over 11. So that gives us that x squared is equal to 121. And because x is obviously positive, we get that x is equal to 11. In particular, this means that this fraction is indeed equal to 1. And you'll notice that this ratio characterizes the ratio between point G and each of these diagonals. So it turns out that point G is actually the midpoint of each of the diagonals. And this helps us a lot because now we can get that the ratio of these similar pairs of similar triangles is equal to 1, and therefore the similar triangles are actually congruent to each other. So I'll erase all of these calculations because they won't be as relevant anymore, because what we get that we really wanted was a new side lengths. So because we know that BG is equal to EG and CG is equal to FG and so on, I'll just write down for consistency that AG is also equal to DG. This gives us that FE is equal to 8, DE is equal to 20, and CD is equal to 11 because of the pairs of congruent triangles. And at this point, calculating the area is not too difficult. All we need to do is find that the side length of the large equilateral triangle, I'll just write down the work here. The side length of the large equilateral triangle is going to be 39. So the area is going to be 39 squared root 3 over 4 minus 20 squared root 3 over 4 minus 11 squared root 3 over 4 minus 8 squared root 3 over 4. And the reason this is the case is because the 39 squared root 3 over 4 is just going to be the big equilateral triangle XYZ. The 20 squared is going to be the equilateral triangle, so I think 20 here, 11 is going to be here, and 8 is going to be here. So you can be confident that this is the answer. And I'll save you the commutation, 234 root 3. And this is the answer to the problem. And I did say I was going to present a bit cleaner of a solution. This solution can be found in the solution packet, but a bit cleaner of a solution is as follows. And so I'll write this new solution out in green. And what I'll do is I'll just write down some ratios that you'll see as apparent because of the similar triangles. So first we have AG over FG is equal to DG, over CG, and AG over BG is equal to DG over EG, and lastly, BG over CG is equal to EG over FG. And I'll do some magic here now. Let's say we multiply each of the fractions. So first, if we multiply all the fractions on the left-hand side, we can get AG times AG times BG over BG times FG times CG is equal to, if you multiply all the fractions on the right side now, which would give DG times DG times EG over CG times EG times FG. And now we can get that the BG's and EG's here cancel out, and the FG times CG in the denominators of each fraction cancel out. So we're left with AG squared is equal to DG squared. And this is exactly how we reach the conclusion that the ratios of the side lengths, or the ratios of G with respect to each diagonal was actually equal to 1 in a bit cleaner solution, although this is a bit more contrived and you wouldn't think to like multiply all these fractions together when you're solving this problem for the first time. But this is definitely like a cleaner method.